Welcome to this explainer on organic chemistry. Today, we're going to unpack exactly how the complex molecules of life are built from just a few simple, logical building blocks. So if you've ever wondered how the universe constructs everything, from the fuel in your car to the actual DNA inside your cells, well, you're definitely in the right place. Let's get right into it.
Okay, here is our roadmap for today. We've got a 5-step journey, starting with the magic of carbon, then cruising down the hydrocarbon highway. After that, we'll crash a functional group party, take a look through the looking glass at isomers, and finally, wrap up with chemical transformations. So, starting at our macroscopic foundation, Section 1, the magic of carbon. Carbon is special, and it really comes down to a few core traits. First off, tetravalency. With an atomic number of 6, it has exactly 4 valence electrons sitting in its outer shell, meaning to reach that happy, stable octet, it needs to form exactly 4 covalent bonds. Combine that with its relatively small atomic size, which holds onto shared electrons super tightly, and you get incredibly strong bonds. But here's carbon's real superpower: catenation. This is its unique ability to link up with itself to form these endless, highly stable molecular architectures. We're talking everything from long linear chains to massively complex intersecting rings. Now, to form these stable 3D shapes, carbon does something absolutely brilliant: orbital hybridization. It literally mixes its spherical s orbitals and dumbbell-shaped p orbitals to create brand new identical hybrid orbitals. And the geometric outcomes here are highly predictable. Look at this breakdown. When carbon mixes 1 s and 3 p's, you get sp3 hybridization, forming a 3D tetrahedral geometry with angles of exactly 109.5 degrees. That's your standard alkanes. If it mixes 1 s and 2 p's, you get sp2, which lays flat in a trigonal planar shape at 120 degrees for alkenes. And for alkynes, it's just sp, creating a strict linear 180-degree line. These specific geometric angles dictate the physical structure of basically everything in organic chemistry. All right, time for a quick concept checkpoint. I want you to visualize standard methane. That's a single carbon atom bonded to 4 hydrogen atoms. Based on what we just went over, what are its hybridization and ideal bond angle? Well, if you pictured a 3-dimensional pyramid-like structure, you nailed it. The answer is sp3 hybridization, forming a tetrahedral geometry with an ideal bond angle of 109.5 degrees. Every single bond in that molecule is pushing equally away from the others to find perfect stability. Moving right along to Section 2, the hydrocarbon highway. Now that we have our carbon atoms ready to bond, let's start snapping them together. Hydrocarbons are the absolute simplest organic compounds, literally made entirely of just hydrogen and carbon. The primary way we classify them comes down to one thing: saturation. Take a look here. On the left, we've got saturated hydrocarbons, also known as alkanes. These have pure single carbon-to-carbon bonds. We call them saturated because they are holding the absolute maximum number of hydrogen atoms possible. No room for any more. Now, on the right, we have unsaturated hydrocarbons, your alkenes and alkynes. Because these feature double or triple carbon bonds, they actually have to sacrifice potential hydrogen atoms just to form those extra links between the carbons. To successfully navigate this highway, you absolutely have to know the street signs. And in our case, those are the universal IUPAC naming prefixes. It's a structural skeleton you just need to memorize. 1 carbon is meth, like methane, 2 is F, 3 is prop, 4 is bute, and 5 is pent. So, for example, if you see a molecule with 3 carbons and all single bonds, boom, you instantly know it's propane. If it had a double bond, propene. This prefix system is literally the universal language of organic chemistry. But pure hydrocarbon chains are actually pretty nonpolar and, frankly, chemically boring. So let's jump into Section 3, functional group party, and introduce some VIP guests. Enter the functional group. Think of functional groups as highly specific chemical accessories that attach to the basic carbon skeleton, which we usually represent by the letter R in formulas. The exact moment one of these groups attaches, it completely overrides the boring nature of the hydrocarbon. It gives the entire molecule a unique, reactive personality, dictating its boiling point, its polarity, and exactly how it's going to interact with the world around it. When you categorize these functional families, you can really see how quickly the rules of the game change. By just swapping out a hydrogen atom for a hydroxyl group, an OH, you instantly create an alcohol, making the molecule polar and water-soluble. Swap in a carboxyl group, you've got a weak acid. Attach an amino group featuring a nitrogen atom, and suddenly you've created a weak base. literally the very foundation of the amino acids that build the proteins inside your body right now. Finally, the carbonyl group, which is a carbon double bonded to an oxygen, brings intense polarity to ketones and aldehydes. The carbon skeleton is just the vehicle, but these functional groups, they're the ones driving. Let's do another quick concept checkpoint to test your functional group recognition. Can you identify the specific organic family defined by a terminal carbon, meaning it's at the very end of a chain, that is both double bonded to an oxygen and single bonded to a hydroxyl group? Any guesses?
Well, if you combined the carbonyl and the hydroxyl in your head, you got it. That configuration creates carboxylic acids. Because of this really specific arrangement, these molecules can easily donate a proton in an aqueous solution, making them weak acids. This is actually the exact family responsible for the acetic acid you'd find in your kitchen vinegar.
All right, moving on to section 4, mirror, isomers. Now that we know the parts, we really need to look at spatial reality. See, just possessing the exact same building blocks doesn't necessarily mean they are assembled the same way. Welcome to the world of isomers. Isomers share the exact same molecular formula, meaning the exact same raw count of carbon, hydrogen, and oxygen atoms, but they are profoundly different molecules. On the left here, we have structural isomers. These connect differently at a basic structural level. You might have a straight chain versus a branch chain, or maybe a functional group attached to carbon number 1 instead of carbon number 2. On the right, we have stereoisomers. Now, these are much subtler. They have the exact same basic atomic connectivity, but they orient themselves drastically differently in 3D space. Let's test your understanding of that 3D space real quick. Geometric isomers, which are a type of stereoisomers that exist in cis or trans configurations, only happen around double bonds. Why don't we see them around standard single carbon-to-carbon bonds? It all comes down to rotation. Single covalent bonds allow rapid, completely free rotation, kind of like a wheel spinning on an axle. But double bonds, they contain overlapping pi orbitals. Rotating that bond would literally break the molecule apart. Therefore, double bonds restrict rotation, locking the chemical structure into fixed cis positions, where identical groups are stuck on the same side, or trans positions, where they are locked on opposite sides. And that brings us to our final stop, section 5, chemical transformations. We've built our scaffolds, added our functional groups, and locked them into 3D space. Now it's time to put it all into motion. I know organic reactions can sometimes look like absolute alphabet soup, but most actually follow one of 3 really logical pathways. First up is the addition reaction. Take an unsaturated molecule like ethene, which has a double bond. Those pi bonds are relatively weak, so under the right conditions, they basically break open like a pair of swinging doors to accept incoming atoms, in this specific case, hydrogen gas. The 2 molecules just combine to form a single, larger, completely saturated molecule called ethane. Next, let's look at our second pathway, the substitution reaction. If addition is combining, substitution is essentially just a functional swap. When methane reacts with chlorine gas under ultraviolet light, it literally trades one of its hydrogen atoms for an incoming chlorine atom, creating chloromethane. The skeleton stays perfectly intact. We basically just swapped out a piece of the furniture. Lastly, we have the elimination reaction, which works entirely in reverse of the addition reaction we saw just a minute ago. Here, atoms or functional groups are systematically removed from adjacent carbons in a saturated molecule. As they leave, the carbons literally have to double bond to each other just to satisfy their tetravalency. We see this perfectly as ethanol is heated with an acid catalyst, effectively eliminating a water molecule and leaving behind unsaturated ethene gas. As we wrap up this explainer, I have a challenge for you. Take a second and just look at the world around you right now. The plastic of your device, the clothes on your back, the literal DNA replicating in your cells as we speak. Can you picture the invisible, hybridizing carbon scaffolds holding it all together? Organic chemistry isn't just a set of rules on the page. It is the elegant, logical architecture of life itself. So, what other invisible structures are hiding in plain sight in your everyday life? Something to think about. Keep questioning, keep observing, and thanks so much for joining me today.